Hello, everyone. Today we're going to be starting chapter 3, and we're going to start the chapter talking about extrema on an interval. So if you read through the notes, which I'm sure you will all do, we can see that having a minimum or a maximum on a function is considered extrema. So you have all witnessed this before in your lives. Take, for example, a parabola. So if we have a parabola, we have studied before that the vertex of a parabola can either be a minimum or a maximum value. So in this case, our parabola is facing up, which means that we have a minimum value. So we call something a minimum value if that y value is less than any other y value on the function. Which makes sense because if we take a look at this, its y value could maybe be, I don't know, -2, and all the other y values of that function are above it. We've also seen parabolas before that are facing down. Well, maybe this guy right here. And his vertex would be a maximum value because that y value is greater than any y value of the function. So we're going to use a couple new terms today. One is absolute minimum and absolute maximum, which is that y value is the highest y value on that entire function over a certain interval. So if we look at a parabola, the intervals that we're looking at right now are -infinity to infinity. And we can say, okay, over that interval, we know that this has a minimum at whatever the vertex is. And same for this right here. All right. But let's say we had a function and we wanted to cut it off at a certain interval. So for example, the function I drew below, we can see that this looks like it has two values that could be the maximum values, either this value up here or this value up here. But let's say that we only want to look between the x values of A and B. So if we look between those two x values, then we see that the absolute maximum we're looking for is up here at this point because we only care about the y values in between the interval A and B. So the question is, how do we use calculus to determine what these absolute maximums and absolute minimums are? So if you remember, we know that the derivative at a min or a max is always 0. Because if we draw a tangent line there, then we always have a slope of 0. So that can definitely help us find mins and maxes. So now we're going to take a look at some pictures of some functions to determine the absolute max and the absolute min. So now when we're trying to find the absolute max or the absolute min, it is important to know whether the interval is open or closed. If we have a closed interval, that means that there are brackets around our x values, like for example, the interval -1 to 2, which means it includes those x values. If there are parentheses around those x values in the interval, that means it does not include those x values. So if we take a look at our first picture, we are given the closed interval -1 to 2, which means that the y values of -1, 2 and 2, 5 are included in this function x squared plus 1. So if we're looking at this picture, we definitely have a minimum value at 0, -1, and then we would have a maximum value at 2, 5 because the endpoints can be included in our absolute min or absolute max. So this function right here, x squared plus 1, is being cut off at -1 and 2. So we're only looking at this part of the function. And we want to determine what is the minimum y value and what is the maximum value just within this interval between -1 and 2. So now let's take a look at the version where the endpoints are not included. So if the endpoints are not included, what we do is we draw some open circles at -1 and at 2. So because there is an open dot at 2, 5, it is not considered an absolute max. And in fact, we don't have an absolute max because these y values are getting closer and closer and closer to 5, but not reaching it necessarily. We do definitely have an absolute minimum at 0, 1. So if our endpoints are included in our interval, we can have an absolute maximum or an absolute minimum at those endpoints. If they're not included, then we can't have an absolute max or absolute min. However, we still have an absolute min within the interval at 0, 1. Now let's take a look at another example of a different function that looks really similar, but it's changed a little bit. So the function is not continuous on the interval -1 to 2. So this function has a point of discontinuity at x equals 0. Because this function is not continuous over the interval -1 to 2, it cannot have a maximum or minimum point. However, it can have an absolute max or an absolute min at the endpoints. So this has an absolute maximum at the point 2, 5. So now we're going to talk about something similar but slightly different than absolute extrema or absolute max and mins. We're going to talk about relative extrema. And in a nutshell, relative extrema are points that are at the top of a hillside or at the top of a turning point. It does look like a maximum, but there could be multiple relative extremas in one interval. Or it's at the bottom of a valley. So let's take a look at a picture where we have a relative max and a relative min. For this function, we have a relative maximum at 0, 0, and we have a relative minimum at 2, -4. So this interval is over the interval -infinity to infinity, and there actually is no absolute min or max because this function would just continue on forever to positive infinity and down to -infinity. However, we do have a top of a hill right here and the bottom of a valley right here, so those 2 points are considered relative extrema. In this next function, we have a relative maximum, but we have no relative minimum. And it looks like that we definitely come to the top of a hill right here at this point, 3, 2, and then the function is just going to keep descending down. So it is important to note that points can be labeled as an absolute or relative max or min. So any point within an interval could be an absolute max or a relative max. However, you cannot have relative mins and maxes at endpoints. You can only have absolute mins and maxes at endpoints. This brings us to a very important concept in calculus, a critical number. So a critical number occurs where the derivative at a certain x value either does not exist or equals 0. This is really important because if a derivative does not exist at a certain point, it could be either a maximum or a minimum like we see in this first picture. Also, if the derivative equals 0, it could be a maximum or a minimum. It doesn't necessarily have to be, but it could be. So that's why we want to recognize where the derivative either equals 0 or is undefined. And in theorem 3.2, a relative minimum or relative maximum at x equals c is a critical number of f. So relative minimums and relative maximums are critical numbers. So we're going to go ahead and take a look at this function and find all of the critical numbers for g of x equals x squared times x squared minus 4. So I want to find where does the derivative either equal 0 or where is the derivative undefined. So first thing I'm going to do to make finding the derivative a little bit easier is distribute the x squared, so I get x to the 4th minus 4x squared. And now I'm going to take the derivative and get 4x cubed minus 8x. And so now I need to think about where can this derivative equal 0 or where is it undefined. So because I have the derivative 4x cubed minus 8x, it's not going to be undefined anywhere. It's a continuous function. But I can find where this would equal 0. So I'm going to take my derivative, set it equal to 0, and factor out a 4x, and take each factor and set it equal to 0. And I know that I will have a critical number at x equals 0, and at x equals plus or minus the square root of 2. Now let's try the same thing for the function f of x equals x to the 1/3 on the next page of the notes. So if I think about x to the 1/3 or the cube root of x, I don't have any restrictions on the domain. Since it's a cube root, I can plug in positive and negative numbers. So now I want to find the derivative and see where that equals 0. So f prime of x will equal 1/3 x to the negative 2/3, which is 1 over 3x to the 2/3, or 1 over 3 times the cube root of x squared. So if I think about this derivative, 1 over 3 times the cube root of x squared, this is actually not going to equal 0 anywhere. We know this because if I tried to set this equal to 0 and multiplied by 3 times the cube root of x squared to the other side, I would get 1 equals 0, which does not work. However, I think that this derivative will be undefined at some certain x values, because if the denominator equals 0, then the derivative is undefined. So I am going to take my denominator and set it equal to 0. And I know that x to the 2/3 equals 0 when x equals 0. So I will have a critical value at 0, at x equals 0. Cross that out. Because the derivative f prime of x is undefined at that point. Now let's take a look at the function f of x equals 4x over x plus 1. So it's important to note that for this function, x cannot equal -1. So -1 is not in the domain of our original function, which is step 3, restrictions on the domain. And it's important to note that because if we get a critical number at -1, it actually can't be a critical number because it's not in the domain of our function. So what we're going to do is take the derivative and set it equal to 0 and see if we can find a critical number that way. So the derivative is going to be, using the quotient rule, 4 times x plus 1 minus 4x times 1 all over x plus 1 squared. And if I simplify that a little bit, I will get 1 over x plus 1 squared. Okay, so now if I take a look at my derivative, again, this derivative will not equal 0 anywhere because, again, if I set it equal to 0, I'll get 1 equals 0. However, this derivative will be undefined whenever the denominator equals 0. So f prime of x will be undefined when x plus 1 squared equals 0. So that would be x equals negative 1. However, like I said before, negative 1 is not in the domain of our function. So negative 1 cannot be a critical value. So in this example, we have no critical values, which means that this function will not have any relative maximums and relative minimums. This makes sense because if we graphed this function, we would have a horizontal asymptote at 4. We would have a vertical asymptote at negative 1. And the function would look like this, if you remember your Algebra 2 pre-calculus days. So if we take a look at this function, it kind of makes sense that this function does not have any relative mins or relative maxes. There's no hills and there's no valleys. So now that we know how to find relative maxes and relative mins and critical points, we can now determine what is a relative min, relative max, or an absolute max, or an absolute min. So we have a step-by-step test that can help us determine what these x values are and the y values. So the first thing that we want to do is determine what interval are we looking over. And we're looking over the interval negative 1 to 2 for this function right here. So what we want to do is set up our table and have negative 1 as our first x value, 2 as our last x value, and any critical values that we find in between the interval we can put in the middle of the table. Next, we want to find any critical numbers to see if there's any relative maxes or relative mins. So to find the critical values, we first need to take the derivative of our function, which is 12x cubed minus 12x squared. And we can set that equal to 0. It won't be undefined anywhere because it's a continuous function, so we don't have to worry about that. And we find that we have critical values at x equals 0 and at x equals 1. So I'm going to take those two x values and put them in my table. And so now what I can do is I can plug in those 4 x values into my original function, and then I can just see if there's any absolute maxes, which would be the highest y value, absolute mins, or relative maxes or relative mins. So let's go ahead and plug all those in. So if I plug in a negative 1, I would get 3 times negative 1 to the 4th minus 4 times negative 1 cubed, which would be 3 plus 4, which is 12. If I plugged in a 0, I would get 3 times 0 to the 4th minus 4 times 0 cubed, which is just 0. I plug in 1, I get 3 times 1 to the 4th minus 4 times 1 cubed, which would be a negative 1. And then if I plugged in a 2, 3 times 2 to the 4th minus 4 times 2 cubed. Oh, this is hard math. 3 times 16 minus 4 times 8, which would be 48 minus, what is that, 36, which equals 12. So it looks like I have two absolute maxes. So I have an absolute max at -1, 12, and another absolute max because they're equal, so that's okay, at 2, 12. And then it looks like I have an absolute min at 1, -1. Let's try it with our next example. We want to find the extrema of f of x equals 2x minus 3x to the 2/3. So since we want to find it over the interval, -1 to 3, the interval will always be given. We would put a -1 as our first x value, 3 as our last x value, and now we want to find the critical points in the middle. So I am going to take the derivative. So f prime of x will equal 2 minus 2x to the -1/3, which is, if I factor out a 2 times 1 minus 1 over x to the 1/3. Okay, so now I want to determine where this function or where the derivative either equals 0 or is undefined. And we can easily see where this function would be undefined. Since we have a variable in the denominator, it will be undefined at x equals 0. So I know I can take a 0 and put it into my table. I also want to determine where this function will equal 0. So I'm going to take 2 times 1 minus 1 over x to the 1/3, set it equal to 0. So that will be 1 minus 1 over x to the 1/3 equals 0. So 1 can equal 1 over x to the 1/3. If I multiply the x to the 1/3 to the other side, I'll get x to the 1/3 equals 1. And if I cube both sides, I get x equals 1. So f prime of x will equal 0 when x equals 1. So those are my two critical values. So now all I have left to do is plug those four into the original function and see what my highest y values are and what my lowest y values are. So I have 2 times -1 minus 3 times -1 to the 2/3, which is -2. If you cube root -1, you get a -1, square it, +1. So -2 minus 3 would be -5. If I plug in a 0, I will just get a 0. If I plug in a 1, I will get a 2 minus 3, which is a -1. And if I plug in a 3, I am going to get a crazy nasty number. Let's see. This will be 6 minus 3 times the cube root of 3 squared. So we need to determine if this is going to be a positive number or a negative number, because if it's positive, this will be our maximum. So we really have 6 minus the cube root of 9, and the cube root of 8 is 2, so it'll be slightly bigger than 2. So this will be our y value. That is our maximum. So we have an absolute maximum at 3, this crazy number, and we have a minimum value, an absolute min, at -1, -5. We can't determine if 0 and -1 are relative mins and relative maxes yet. We need to do a little bit more calculus in later sections to be able to figure that out. So these problems, you're just working on absolute mins and absolute maxes. And we can't end our calculus fun day without doing some trig. So we are going to find the extrema of 2 sine x minus cosine 2x on the interval 0 to 2 pi. So I'm going to take a 2 pi and put it at the very bottom of my table. And I am going to need to take a derivative of that function to find my critical points. So f prime of x is going to equal 2 cosine x minus, we need to chain rule, so that's going to really be a plus 2 sine 2x. And I need to set this equal to 0 and solve. So 2 cosine x plus 2, I'm going to change that sine 2x to a 2 sine x cosine x. And then I can go ahead and factor out a 2 cosine x. And that will leave me with a 1 plus 2 sine x equals 0. And then I need to take both pieces, set it equal to 0, and solve. So I know that cosine x equals 0 at pi over 2 and 3 pi over 2. And sine x equals negative 1/2 at, let's see, bottom 2 quadrants, opposite over hypotenuse. So that would be a 30-degree angle, which is the pi over 6's. So this will be 7 pi over 6 and 11 pi over 6. So those would be my 4 critical values that I would need to put in the middle. So we have a pi over 2, a 7 pi over 6, and an 11 pi over 6. And so now we do need to take all 5 of those and plug it in and find our maxes and our mins. So if I plug in a 0 first, I will get a 2 times the sine of 0 minus the cosine of 0, which is, sine of 0 is 0, minus 1, which is negative 1. Probably want the unit circle for all this stuff. Let's do it really quick. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, so now let's do pi over 2. So 2 times the sine of pi over 2 minus cosine. 2 times pi over 2 is pi. So that would equal 2 times 0, which is 0, minus cosine of pi, which is negative 1. So we would get a 1. All right, 7 pi over 6, next on the list. And 2 times 7 pi over 6 would be 7 pi over 3. Ooh, let's come back to that. Let's plug everything in and we'll come back. We probably need to do some unit circle stuff. So this will be 2 times the sine of 11 pi over 6 minus the cosine of 11 pi over 3. And this will be 2 times the sine of 2 pi minus the cosine of 4 pi. And that should be the same as 0 because it's coterminal angles. So we'll also get a negative 1 there. All right. So the sine of 7 pi over 6, we already know that that is negative 1/2. So times 2 will be a negative 1. And we know that the sine of 11 pi over 6 is negative 1/2. So times 2 is negative 1. So let's do the cosine of 7 pi over 3, which is the same as a pi over 3, which is a 60-degree angle. So this will be a 1, this will be a root 3, and this will be a 2. So it'll be 1/2. So that'll be a minus 1/2, which is a negative 3/2. And then 11 pi over 3 is the same as 5 pi over 3, which is down here. So this will be a negative root 3. So that'll be minus 1/2 again, which is again negative 3/2. All right. So it looks like we have some absolute mins. At negative 3/2, and we have an absolute max at pi over 2 comma 1.